Welcome back, chemistry students. We are going to have two lessons focusing on thermochemistry. So thermochemistry is the study of energy, specifically heat changes, during a chemical or physical process. So in lesson 1 of thermochemistry, we're going to review parts of a heating curve. We are also going to identify different areas on the curve that require different types of calculations. And lastly, we are going to use Q equals mc delta T to solve specific heat capacity and calorimetry problems. In lesson 2, which will take place next week, you're going to calculate energy changes during phase changes using molar heat of fusion and molar heat of vaporization. Before getting into specific heat problems, we are going to review the interpretation of heating curves. So heating and cooling curves show the energy changes that occur as a substance goes from a solid to a gas as temperatures change. So you probably remember from solid to liquid, the phase change of fusion or melting occurs. From liquid to gas, the phase change of vaporization or boiling occurs. So fusion and vaporization, they're absorbing heat, and so these are endothermic processes. As we go from gas to a liquid and it cools, condensation occurs, and then liquid back to solid, solidification or freezing occurs. Condensation and solidification, they are releasing heat, and so they're considered to be exothermic processes. And you can also see on the heating curve graph the particle movement and how it changes from solid to liquid to gas. So if you notice down on the heating curve graph, once the ice has warmed to 0 degrees Celsius, the added energy begins to break the bonding that keeps the water molecules in place. Notice that there is no temperature increase or decrease while the solid water is changing states. The energy used in this phase does not cause the temperature to rise. Instead, the energy goes into the melting process. Both the solid state and the newly formed liquid state are at equilibrium during melting, and this means that the temperature stays constant. You will find that temperature stays constant during all phase changes. So during solid, liquid, and gas phases, we are able to use Q equals mc delta T to calculate things like heat, mass, specific heat, or temperature changes. However, in the flat portions of the heating curve, which represent the phase changes, we do not use the specific heat formula. Instead, we use heats of fusion and vaporization to calculate those energy changes during the phase changes. And so heats of fusion and vaporization, that is the heat required to melt 1 mole of a solid substance. So for example, using the heat of fusion, we could calculate the heat absorbed as a substance melts. So you're going to learn next lesson how to use heats of fusion and vaporization. In this lesson, we are totally focused on specific heat, which we will define in the next section of our lesson. It's important to know that different substances respond to heat in different ways. If a metal chair sits in the bright sun on a hot day, it might become quite hot to the touch. An equal mass of water in the same sun will not become nearly as hot. So we would say that water has a high heat capacity, the heat capacity being the amount of heat required to raise the temperature of an object by 1 degree Celsius. Water is very resistant to changes in temperature, while metals in general are not. So the specific heat of a substance is defined as the amount of energy required to raise the temperature of 1 gram of the substance by 1 degrees Celsius. So it's going to take a lot more energy to raise the temperature of water opposed to raising the temperature of, say, gold, lead, or mercury. So you can see this in the chart presented here. water has a specific heat capacity of 4.186 joules per grams degree Celsius. We can compare that to something like bismuth, which has a much lower specific heat capacity of 0.123 joules per grams degree Celsius. So it does not take as much energy to raise the temperature of bismuth. So bismuth does not resist change in temperature like something such as water would. So before we get into some practice problems, we're going to break down the formula, define some of the parts and the units before moving forward. So first of all, the joule is the metric unit of energy. 1 kilojoule is equivalent to 1,000 joules. A calorie, with a lowercase c, is the amount of energy needed to raise 1 gram of water exactly 1 degree Celsius. So it takes 1,000 calories with a lowercase c to make up 1 calorie with an uppercase C. That's the calorie we think of in food labels. So if you see calorie with an uppercase C, that's referring to food labels. Lowercase c is referring to 1,000 calories. And 1 lowercase c calorie is equal to 4.184 joules. So we defined specific heat capacity before as the amount of energy needed to raise 1 gram of a substance exactly 1 degree Celsius. So the symbol for specific heat capacity is C, and the units is joule per gram degree Celsius. We are going to use this equation, Q equals mc delta T, and we're going to be solving for some different things. We might be solving for Q, which is the heat absorbed or released in joules. We might be solving for C, which is the specific heat capacity. M is the mass in grams, and then change in T, that's the temperature change. And we can find this by taking the final temperature minus the initial temperature. And we always use absolute values in that calculation. Another thing to keep in mind, temperature, it can be measured in Celsius or Kelvin for this equation. We are also able to find the energy change experimentally in the lab by using something called a calorimeter. And it's just an insulated device, and it's used for measuring the amount of heat absorbed or released during a chemical or physical process. So you can read the before temperature, the after temperature to plug in for the delta T. You have the specific heat of the substance in the calorimeter, and then you would also have the mass of the substance in the calorimeter. And so you could take your information from the lab and calculate the heat absorbed or released. We are going to walk through a few practice problems together. So you have your equation at the top and then some explanation of the variables. So the first sample problem says a 500 gram sample of iron changes from 22 degrees Celsius to 35 degrees Celsius. The specific heat of iron is known to be 0.46 joules per gram degree Celsius. How much heat was added? So first we need to write down our formula, and then we need to figure out what we're given. So we can list on the side Q, M, C, and delta T. So they have not given us Q. That's what we have to solve for. They have given us the mass of 500 grams, the specific heat of 0.46 joules per grams degrees Celsius, and they've given us the change in temperature. We went from 22 to 35. So to figure out the change in temperature, you would take 35 minus 22, and that would come out to be 13 degrees Celsius. So after we've identified everything we have, we can now plug it into the formula. So when we plug it into the formula, it looks like this. Q equals 500 times 0.46 times 13. So when we plug that into our calculator, we get 2,990. We're limited to 2 significant figures, so we have to round it to 3.0 times 10 to the third power joules. The second problem says a 400 gram sample of water changes from 24 degrees Celsius to 35 degrees Celsius. The specific heat of water is known to be 4.18 joules per grams Celsius, how much heat was added? So I'm going to pause the video for a second, and I want you to pause it on your end as well. And I want you to try this one on your own. See if you can identify the variables that you're given. Try to identify what you're trying to find. Plug it into the formula and see if you can get to that answer. So we write down our formula. You should have found the mass to be 400 grams, the specific heat to be 4.18 joules per grams degrees Celsius, and then the change in temperature, when you subtract 35 minus 24, you should have got 11 degrees Celsius. So we're looking for Q in joules, the heat in joules. If you plug everything into the formula, you should have got 18,392, which we're limited to 3 significant figures, so that rounds to 18,400 joules. Number 3 says, when 82 joules of heat is added to a sample of aluminum, its temperature increased by 15.3 degrees Celsius. Given that the specific heat capacity of aluminum is 0.90 joules per grams degrees Celsius, what is the mass of the sample? We're going to be using our specific heat capacity formula, Q equals mc delta T. We need to identify what we've been given. We have been given 82 joules, which is Q. We've been given a change in temperature. It says the temperature increased by 15.3 degrees Celsius. So that's actually going to be delta T. We've also been given specific heat capacity, 0.9 joules per grams degrees Celsius. So in this case, we are going to be looking for mass in grams. We're going to be solving for mass, and we're going to do so using simple algebra. So we need to plug everything into the formula. It would look like this. We're trying to get m by itself. We're trying to isolate m. So we need to divide 0.9 times 15.3 on both sides of the formula so that we can get m alone. So we're going to do that on both sides of the formula. And you can see here that when we do that, it cancels out on the right side of the formula. And in our calculator, we just have to punch in 82 divided by, and then in parentheses, 0.9 times 15.3 parentheses. And when you do that in your calculator, and you're solving for m, you get 5.95497. We are limited to 2 significant figures, so we have to round that to 6.0 grams. So take a second now. I'm going to read number 4, and then I want you to try it on your own before you watch me do it. So it takes 78.2 joules to raise the temperature, 45.6 grams. Sorry. It takes 78.2 joules to raise the temperature of 45.6 grams of lead by 13.3 degrees Celsius. You're going to calculate the specific heat capacity of lead. So pause the video and try it by yourself. Okay, we're going to be using our formula. We can identify Q is 78.2 joules, mass is 45.6 grams. We're trying to find specific heat capacity, and the change in temperature is 13.3 degrees Celsius. So if we plug all of those into the formula, we're going to be solving for C. We need C to be by itself. So we're going to divide each side by 45.6 times 13.3 to get C by itself. Another option, you could multiply 45.6 grams and 13.3 and then solve that, multiply those together and then divide out that number. It's kind of your choice. There's more than one way to solve an algebra problem. So if you do it my way, you would take 78.2, divide parentheses, 45.6 times 13.3 parentheses, press enter on your calculator, and the specific heat capacity comes out to 3 significant figures as 0.129 joules per grams degrees Celsius. Our last problem is the challenger. It says a 142 gram sample of silver at a temperature of 19.6 degrees Celsius absorbs 61.30 joules of heat. What is the final temperature of the sample? And then they give you the specific heat capacity of silver. It is 0.24 joules per grams degrees Celsius. So take a second now and write down everything you've been given in your formula. Pause the video, and then we will go from there. So there's our formula, and this is everything we've been given. We have been given one temperature, but not the other. So which one have we been given and which one are we trying to find? Well, it says that a temperature of 19.6 absorbs 61.30 joules of heat. Then it says, what is the final temperature of the sample? So we've been given the initial temperature. We're trying to find the final temperature, and we're going to label that as TF. We're trying to calculate the final temperature. So we're going to plug in everything that we have into the formula. So it kind of looks intimidating, but it is not difficult to solve. The first thing you want to do is try to get TF minus 19.6 by itself first. So we need to divide each side by 142 times 0.24. So when we do that, that actually cancels, and we are left with this. So in our calculator, you will do 61.30 and then divide it by parentheses 142 times 0.24. And when you do that, that will give you 1.7987, and it keeps going from there. I just stopped the decimal there. Equals final temperature minus 19.6. So now we need to get the final temperature by itself. So to get rid of that minus 19.6, we need to add 19.6 to both sides. If you do it to one side, you have to do it to the other side. Those are the rules of algebra. So we're going to add 19.6 to both sides. So the final answer for the final temperature to 3 significant figures comes out to be 21.4 degrees Celsius. So this week for your assignment, you're going to be completing for week 5, day 2, you're going to be completing a University of Texas assignment, and please reach out if you need any help. Have a great weekend.